Good morning. So let us continue with the lectures of theory of fire propagation. We will now move on to the third module, which is the review of premixed and diffusion flames. We have already seen that fires are basically turbulent non-premixed flames because they involve reactants, fuel and air, which are usually not well mixed before the combustion occurs. So they are non-premixed or diffusion flames and they are turbulent also in nature. If you take the solid and liquid state fuels, for example, you know that the major reactions take place in the gas phase, so that for the first steps will be the gasification of these fuels, solid fuel or liquid fuel, to generate the gaseous fuels which will take part in the combustion reactions in the gas phase. So that means there is a limited chance that the premixing between the air and these vapors will occur. So due to which these are non-premixed flames. The phase change or the gasification, so generation of the pyrolysis gases or the vapors is the first step. For that, heat feedback also is required. The heat feedback basically continues to evolve the fuel vapors, and in the gas phase the combustion sustains due to the transport of the fuel vapors or the gases from the condenser phase to the flame, and from the ambient air comes to the flame in the diffusion transport, or being aided by the turbulent transport, convective transport. So that means that whenever the mixing between the fuel and gas, fuel gas and the air takes place at stoichiometric proportions, the flame zone is formed at that particular location. So the mixing also is the one of the step. The first step is the generation of the fuel vapor. Second step is the mixing of the fuel and the oxygen from air to form the flammable mixture. So this is the second step, and when they mix at stoichiometric proportions, the chemical kinetics is so fast that they consume the chemical reactions consume the mixture, flammable mixture immediately. So this mixing process, which is the second step, is controlled by diffusion predominantly, because the convection may be in one direction, but the diffusion occurs in the opposite direction to the or perpendicular direction to the convection, so that the diffusion dominated transport of fuel as well as the oxidizer take place. Of course, it will be aided by the convection or turbulent eddies. The faster mixing will occur when there is a turbulent environment. Okay, the mixing process is the second step. When turbulence is involved or convection is involved, the mixing will be enhanced by very high magnitude. The diffusion is molecular level, the mixing etc. will be very fast, so that the molecular diffusion process will be enhanced by several orders. So if you see the diffusion, the time for diffusion will be order of magnitude larger than the turbulence. Even the turbulent mixing will be having a time scale which is much larger than the chemical reaction time scale. So in all these cases, the chemical reaction will be much faster. So what we can primarily conclude is the transport processes such as diffusion and convection etc. are the primary controlling processes for the fires. And not only the mass transport is mentioned here, the heat transport from the flame to the surface also is very important. So that also is predominantly by conduction very near to the surface, and the flame can radiate its heat to the surface and so on. So multiple modes of heat transfer will take place from the flame. The heat flux from the flame to the surface, which is a fraction of the overall heat release, is also important to sustain this. So, the multiple steps involved are the creation of the gaseous fuels, which is due to pyrolysis or evaporation, then the mixing of the gaseous fuel with the oxygen from the air, then the heat feedback to the surface. Now, let us consider a case of fire occurring within a compartment or an enclosure. What happens here is, there is a room which has some doors or windows, some limited ventilation is present. So, in this phenomena, what happens is, due to the available oxygen, some commodities burn, but then due to limited ventilation, the commodities may not be completely burning, or the fuel vapors which are hot enough will be generated. So, that is one phenomena. But if some ventilation is, proper ventilation is present, then what happens is, the fuel vapors are formed, they mix and form a flammable mixture, and this fire can cause what is called a flashover. That is, the neighboring commodities also will be ignited due to this heat release from this fire. Now, what happens is, if there is a heat which is causing pyrolysis alone in the next commodity, for example, that one commodity is burning in a room, and the heat release from this particular burning commodity causes pyrolysis in the next commodity, which is neighboring material, where the fuel vapors are first released. Now, it can happen that the fuel vapors which are released from the second commodity can premix with the air, and deflagrations can occur. That means the premixed reactant in the next commodity can be ignited and deflagration can occur. So, this deflagration is a premixed combustion. Similarly, when the premixed reactants can open a vent and go out, they can form fireballs. So, we can see that a compartment fire, which preliminarily a non-premixed fire, can start, flashover can occur, or deflagration can be initiated, and fireballs can also result. So, the situation here calls for the fuel vapor and oxygen to be mixed before they burn. So, this scenario basically leads to premixed combustion or premixed flames. So, we need to know about the characteristics of premixed flames also. And also, if you take some explosion compartment, etc., for example, a spherical volume where we do tests for flammability and so on, or flame speed measurement, etc., you will see that the pressure build-up can occur here. So, to understand the explosion, pressure rise due to that, and explosion safety features, to plan them, we need to understand the characteristics of premixed flames. Okay, now, when I say premixed flame, you have, so let us consider a simple example. You have a duct in which a reactant mixture is present, which is flammable. Now, when I ignite this at one of the ends, a flame forms, and the flame travels towards the unburnt reactant mixture. So, this is the unburnt mixture. Unburnt reactant mixture, and it consumes it. So, this we call propagation of a flame. The propagation of a flame through the unburnt reactant occurs at a particular speed. Okay, and this depends on several factors. For example, the amount of reactant mixture which is available for it when it propagates, the temperature of the unburnt reactor mixture and the heat losses which occurs from the passage and so on. So, the rate of flame propagation through the reactant mixture depends upon the reactant temperature, the condition of the reactant mixture itself. Say we can say it is equivalence ratio. If it is too lean or too rich, it may not propagate at faster rate. If it is near to the stoichiometric or slightly rich, it may propagate much faster and so on. So, the rate of flame propagation is called burning velocity or laminar flame speed. Now, the laminar or a subsonic speed propagation of a flame through the reactant mixture is called deflagration. So, what we have given in the beginning, that is nothing but the subsonic propagation of a flame. So, this can be conducted in a lab scale by considering a tube in which I ignite a reactant mixture which is loaded here, and the unburned gases are present in the way the flame propagates, and opposite to the direction the burned gas go away, so that the flame steadily propagates. So, this process is called deflagration, and the characteristics of for a particular propagation is the burning velocity or laminar flame speed, which is SL. The estimate of burning velocity is required to calculate the pressure rise in a compartment or the in any enclosed chamber, which can lead to explosion subsequently. Now, one more important set of parameters what we can look in is the limits of flammability. As I told you, too lean, that is, if there is very limited fuel, more of oxidizer is present, that is called lean fuel mixture, or very rich fuel mixture, limited amount of oxygen is present, but more amount of fuel is present. So, limits of flammability is there should be some amount of oxidizer and fuel should be present which can be ignitable. If it is out of the limits, then we say it is out of the flammability limit. A mixture which is not flammable is called as a mixture which is out of the flammability limits. We will talk about this a little bit later. Then the flame thickness. If the reaction occurs at a very fast rate, then the reaction zone will have a very small thickness, that is called flame thickness. Then another parameter called quenching distance. As I told you in this particular case, when you have a passage through which the flame travels consuming the unburnt reactant, if there is heat loss from this passage, then the heat release in the flame will not be able to ignite the subsequent unburnt reactant, so it will quench. So, there is a particular diameter for this passage which will allow the flame to propagate, and below that it is called quenching distance. We will also see about this. So, now these factors are very important to design the explosion prevention system. Vents to avoid explosion, we can say. So, in summary, even though many processes in a fire is non-premixed combustion, a detailed idea about premixed combustion is also required to completely analyze fire in several scenarios. So, let us see some features of premixed combustion or premixed flames first. First, there is a fuel which can be a gas or a vapor which is thoroughly mixed, uniformly mixed, that is, if you measure the concentration at any location, it is same. So, uniformly mixed with an oxidizer, usually air, but this mixture should be in flammable proportion. As I told you, when you say equivalence ratio, it varies say from 0.1 to say 2.7, it varies. Now, when I have equivalence ratio of 0.1, the mixture need not be ignited, may not be ignited. So, we need a particular value of equivalence ratio, say it is say 0.4, which can allow for the flame propagation. Similarly, when you increase the equivalence ratio slowly, there may be an equivalence ratio of say 2.5, I am giving just some numbers, where the ignition can take place. So, less than 0.4, equivalence ratio of 0.4, for the mixture ignition will not take place. That is, you will not be able to form the flame itself by ignition. Similarly, when the equivalence ratio is more than 2.5, it may not cause ignition. So, the flammable proportion is such that if the equivalence ratio of the mixture is in between 0.4 and 2.5, okay, it's just some numbers, it is dependent on fuel, then upon ignition a flame would initiate. And as I told you, this is a chamber in the below figure where there is a flame, the unburnt reactant was fully there, then ignition occurs at the left side and a flame forms and propagates to the unburnt reactants. So, the burnt gas move like this and flame propagates like this with a velocity called SL. Now, this propagation is when this end is open and the burnt gas are free to move away, then this propagation is called deflagration. Subsonic velocity, SL will be subsonic. So, now the steady flame propagation in subsonic speed which occurs in this is called deflagration or laminar flame propagation, and the velocity itself is called SL. Please understand that normally the flame will propagate consuming the unburnt reactants. That means the unburnt reactants will go through the flame in the perpendicular direction of the flame. So, for example, if you have the reference flame at the flame itself, then you will see that the unburnt reactants are coming towards the flame at the velocity of SL, normal to the surface of the flame. So, that means that I need not always have a flame propagation, I can also keep the flame stationary. So, go to this case of Bunsen burner, where now what I do is, I have a cylindrical burner of some length and I premix the reactants, the unburnt reactant, fuel plus oxidizer in flammable proportions and send that with an average velocity of U. It is nothing but the volumetric flow rate of the reactant divided by the area of cross section of the burner, that will be U, superficial or average velocity. So, it is supplied. Now, what happens is a conical flame is formed. This is a cylindrical burner. So, diameter D, cylindrical burner. Now, this conical flame is formed at the end of the tube, and this conical flame is bright blue in color. I will show this in the next slide. Bright blue in color. Now, what happens is the reactants, I have shown a streamline here. The reactants pass through in a perpendicular direction to the flame and goes away, and this velocity component which is perpendicular to the flame zone is called SL, that is the laminar flame speed. That can be calculated by calculating the half cone angle. Say this is alpha, half cone angle. So, U is the superficial velocity of the reactants into sin alpha will give you SL, which is the perpendicular component to this. And please see that based upon the equivalence ratio of the unburnt reactants, you will see that if the unburnt reactants the equivalence ratio is more than 1, only the part of fuel will burn here because there is excess fuel and more oxygen is required, and the fuel also will come out of this flame and it will take air from the atmosphere and burn as a diffusion flame. So, this is called outer diffusion flame. In the case of lean mixture, that is phi is less than 1, then it will only be the hot gases surrounding the conical flame, which we call plume. So, I can either make the premixed flame propagate through unburnt reactant and consume it, or I can make the flame sit stationary on a port of a burner and calculate the SL. So, the characteristic of a premixed flame is the rate at which it propagates perpendicular to the unburnt reactant, or we can say the rate at which unburnt reactant goes through the flame in the perpendicular direction is called laminar flame speed. So, one more setup what I can show you is the setup in the bottom right, which is nothing but a flat flame. It is called a flat flame setup, where I have a honeycomb structure through which reactants are supplied at a given Phi and unburnt temperature Tu. Now, in order to avoid disturbance from the atmospheric air, I shield it with a nitrogen curtain like this. Surrounding the burner, I put a nitrogen curtain, and now a flat flame is formed. So, now what is the flame velocity here? The area of cross section of the flame is known to me. Volumetric flow rate of the fuel is known to me. So, the volumetric reactants are known to me. So, volumetric flow rate of reactants divided by the area of the flame, that will give you the SL. So, here also I am keeping the flame stationary at a particular distance from the burner port. Here I have a conical flame and ask the reactants to go perpendicular direction to the cone here. In the first case, I allowed the flame to freely propagate over the mixture. So, in all the cases, the characteristics is the SL, that is the laminar flame speed. So, important characteristics of a premixed flame is nothing but the rate at which the flame propagates consuming the mixture, which is a very important parameter for us. And obviously, this will depend upon the configuration. For the same Phi and same Tu, the unburnt reactant temperature, you will see that the SL values measured in this setup where the flame freely propagate, or in the Bunsen burner setup where a conical flame forms, or a flat burner, the values will have variations, because it depends upon the configuration also. Now, let us investigate a few more points about the Bunsen burner flame. As I told you, unburnt reactant at a given equivalence ratio on unburnt gas temperature Tu is sent, and it has a superficial velocity U, and alpha is calculated on off cone angle, and I calculate the SL also. Okay, now the conical premixed flame is luminous, as I told you, not very luminous, but it is actually bright blue color. And basically the luminosity of the flame actually indicates the strength of the mixture or the rate at which reaction takes place. So, as I told you, if U is the average superficial velocity and alpha is the off cone angle, and then the laminar flame speed S, this is actually SL, will be U into sin alpha. We can also calculate the SL as the volumetric flow rate of the reactants divided by the area of the cone, actually basically the area of the flame, the conical flame. That also we can use SL. There will be some difference between the calculation made using the off cone angle and calculation made using this. There will be some difference. Now, surrounding the flame, as I told you, if the incoming mixture is rich, that is, it has some fuel more than the oxidizer required for burning it, then an outer diffusion flame is formed, or else hot gases go out of this flame plume. So, now in this slide, I have shown experimental results of methane air flames of several equivalence ratios starting from 0.7 to about double of that 1.4. The reaction takes place over a Bunsen burner. Please understand that U, the average velocity, is varied, it is not constant, is varied to sustain a flame over the burner, because for a given diameter there should be a particular velocity to anchor the flame. If the velocity is too high, then the flame will lift off. If the velocity is lesser, then the flame can go down to the burner tube itself. So, to avoid and anchor the flame outside, just outside the burner like this, in all these cases, I have to vary U. So, phi is varied, U is varied, and the flames are sustained over this Bunsen burner tube of a given diameter. So, it may be 10 mm diameter, for example. So, now several characteristics can be studied by these photographs. So, this is 0.7 and this is 1.4. So, this is stoichiometric 1.0 and this is slightly rich 1.1. So, now please see the characteristics. If you take 0.7, that means you have excess oxygen. You can see that only cone is seen and there is no outer mantle, etc., outer diffusion flame, etc., because it is already lean. So, what happens? All the combustion is almost complete within this, but because of the lean condition, the flame temperature is expected to be lower, because additional nitrogen is there, additional oxygen is there, it absorbs the heat, the flame temperature decreases. So, the intensity of the flame, the brightness of this blue color is reduced, is seen to be dull. Now, I go to 0.8. Now, what I see is the brightness increases, even though there is no visible outer mantle, etc., the brightness of the flame increases, because again the nitrogen quantity is reduced, the flame temperature increases. So, here flame temperature Tf increases in this case, still here also it increases further. So, this is 0.9. So, if you say 0.9 case compared to 0.8 case, the bright blue color is increased, okay, and the flame height, etc., are different. Please understand that because this is because of the U variation, U is actually varied to sustain this flame, the U is not same, okay. So, anyway, with the help of U only we will calculate SL. Now, if you go to 1 stoichiometric, much brighter, it is much brighter than this, because the Tf again increases further and much brighter inner cone is seen. So, in the lean side, the flame is dull because temperature is low, the reaction rates are low. As you increase the equivalence ratio in the linear side from 0.7 to 1, the flame brightness increases. You can also see the thickness also slightly decreases, because of the if you see the bright blue color, the thickness slightly decreases, indicating that the reaction can occur at a faster rate. These are all because of the increase in the flame temperature in this. Now, go to 1.1. Again you see the similar brightness and similar thickness of the flame, and you can now see a outer mantle, the diffusion flame. Now, here it is dull, but here you can see the lot of reaction occurring beyond the flame also, because at 1.1 good amount of fuel comes out and burns surrounding the conical flame, and the diffusion flame becomes stronger when you go to say 1.2. Here, after this, the brightness again decreases. You can see that the brightness from 0.7 to 1 it increased, and it maintained its brightness, etc., at 1.1. Now, when you increase to 1.2, 1.3, etc., the brightness again decreases of the inner cone becomes fading out. This is because again the Tf decreases as the equivalence ratio increases beyond 1.1, and you can see the good amount of burning as a diffusion flame outside the cone when equivalence ratios increase, because more amount of fuel needs oxygen from the ambient to burn as a diffusion flame. So, these are all double flames. That is, there is a inner premix flame and outer diffusion flame which is surrounding the premix flame. Okay. So, luminosity or the brightness of the flame is associated with the flame temperature, that we have to understand.